All right. Let's see. In this video, we're going to derive a heat exchange rate for the co-current and counter-current heat exchanger. Uh, we have a system here where we have some hot temperature going through this section of the pipe, which sort of drawing a little better. We have this section of the pipe where we have some warm temperature flowing through, and outside of this current, we have it surrounded by a colder temperature that's flowing, uh, that's coinciding with it, right? So what we're going to solve for is an expression to describe the heat exchange rate for this system. So we have to first consider the relationship for the heat of the system and some overall thermal heat transfer coefficient, right? So let's go ahead and find heat. So we have Q over here. And to kind of just start with some beginning equation to describe heat transfer, what we know is that there's going to be some overall heat transfer coefficient multiplied by some change of temperature multiplied by the change of area. So ambiguously, we know that as part of our system. We know that this change of temperature is probably going to be the temperature of the heat minus the temperature of the cold countercurrent, right? So what can we do moving forward from this? It seems like we've already hit a dead end. However, we are chemical engineers and we have done general chemistry, meaning that we are familiar with the term MCAT, meaning mass flow rate multiplied by heat capacity multiplied by the change of temperature equals heat, right? You have some mass flow rate and you have your heat capacity, and depending on the change of temperature, gives you heat, right? So what we're going to do is go ahead and introduce something called the mass flow rate heat transfer, or the heat transfer mass flow rate. So what we're going to say is that for the mass flow rate of the hot temperature multiplied by the heat capacity of the hot temperature, we're going to call this heat mass transfer flow rate C of H. And we're going to do the same thing for the cold current too. We're going to call this C of C. And now what we're going to simplify this to is we have an expression where we have Q equals C of H multiplied by dt of our hot line and Q of Cc multiplied by the change of the cold temperature. Okay, so this is good because if you notice, we actually have a change of temperature expression. We just have it in terms of delta T. But we should, if we take the derivative of this function, we can go ahead and similarly take the derivative of it for d of h and d of c to find the overall accumulative change that we're looking for our system. So what would be an equivalent form? We could say that delta, a change of delta t, which is our change of our system, so some gradient, equals delta T of H minus delta T of C. And you can see this is algebra at this point because we know what delta H and delta T of H and delta C of T of C are. We have oh, I'm sorry. This is not Q. This is delta Q. This is change of temperature. And so what we're going to be left with is, if I do the math here, this should be let's see, this is dt of H is equal to d of q over c of h. I remember rules of thermodynamics state that wherever something is hot, it wants to travel to something cold to establish equilibrium. So we're going to say that this is negative in this case. And if we do the same thing for d of c, we get dq over c of c. And so our delta t in this case is equivalent to negative d of q over C of H minus dq C of C. Okay, so what we're going to do is we're going to go ahead and derive some of the, we're going to go ahead and derive this first expression and kind of break it down so that we can share some like terms. The ultimate goal is that we want uh we want D of Q to be equivalent to something so that we can sub in our new equation that we've gotten in this case. So if we do that, we'll get something like dq equals u, this is going to be d delta t d of a, like crazy. Which should be right. So now what we're going to go ahead and do is, actually, no, wait. That is not right. I'm ignoring a step of this. I know I am somewhere. Let's see. We have dq. Oh, I know what I, okay. So we're gonna go ahead and do, we're gonna do as I said, we're gonna go ahead and derive. This is d of q is u d of delta t d of a. And now we're gonna go ahead and sub in variables, and when we do that, we're actually gonna cancel out d of q here in favor of these coefficients. And we're gonna say that q equal, I mean, yeah, we're gonna get 1 of c of h minus 1 of c of c multiplied by the change of area multiplied by the uh overall heat transfer coefficient, which is then set equal to or just forgot TH go yep right. U delta T, which is then set equal to our change of delta T. Yes, okay. This is where we're supposed to be. Because now what we can do is we can do separable equations to get two integrals. If I divide both sides by delta T, I'll get something like d of delta T over delta T equals U 1 over C of H minus 1 over C of C divided by delta A. And now what I can do is integrate both sides for delta T and delta A. So we can see on the left side in this case, I marked it over here. Our beginning position is 1 and our ending position is 2. So we're going to integrate from 1 to 2 to find this gradient. And when we do, we get natural log of T2 over T1, or change of T2 over change of T1 equals U multiplied by A. And this is supposed to be negative because we had a negative before. Sorry. Negative U times A, which is our actual area for the system if we took the derivative of it over 1CH minus 1CC. Okay, so now what we're going to go ahead and do is we're going to go ahead and solve for an equivalent term here. So we know that C of H and C of C, when we originally solved for it, was something like Q of C equals C of H. So I'm going to go ahead and I need to get myself in space. So it was negative Q equals negative C of H multiplied by TH2, or sorry, TH1 minus TH2. And that Q was similarly C of C multiplied by T of C1 minus T of C2. If we go ahead and plug in these functions to our new equation that we have here, we get something like T delta T, or natural log of delta T of 2 over delta T of 1 equals negative U of A over, and then this should be TH1 minus TH2 over C of H minus 1 over, or plus, sorry, and then this turns into a plus, cancel out negative, and then this turns into let's see here. This turns into T C of 1 minus T C of 2. C of C. Oh, wait, no, sorry. Over Q, over Q. I just did my thermo final, so forgive me, my algebra is a little bit spotty right now. My brain is fried. In college terms, it is completely fried. Um, so now what we're going to go ahead and do is define our changes of temperature. We're going to say that change of temperature 2 is actually equivalent to T of H2 minus T of C2, and that T of 1 equals T of H1 minus T of C1, which makes sense for terms of change of temperature. And when we do that, and go ahead and we can go ahead and move Q to the beginning coefficient and divide by natural log. When we do that, we're going to get something like Q equals Q of A multiplied by the change of temperature 2 minus change of temperature 1 over this would be natural log of delta 2 over delta T of 1. Oh, sorry, this is plus. And this is our log mean for our function. All right, for this last part of the video, we're going to go ahead and explain the heat exchanger effectiveness and how this can be used in conjunction with NTU and C minimum and C maximum, aka our heat mass transfer or heat mass transfer minimum and maximum. So I kind of put some red arrows here to kind of detail what we're really looking for. Ideally, what we are looking, or it's not ideally, sorry, I shouldn't say that. What we're looking for in this case is we're trying to say, uh, we need to find an equation where we need to, or where you can find the efficiency of your heat transfer and determine what your best target outcome would be if you change the area or the overall thermal transfer coefficient, whatever parameter you may want, so that you know what size you need your system to be to maximize the efficiency of your system. So, or your heat transfer system. So, what we're going to do is we're going to do the engineering classic of defining efficiency as something of your actual over your maximum. And in this case, what we're going to do is we're looking at heat transfer. So what we're going to be wanting is the Q actual over the Q maximum in this case. So basically, how much heat are we actually transferring over versus what is the maximum of this? So the way that we can imagine this is we said Q is equal to some heat mass transfer, H, multiplied by, in this case, it would be the temperature in minus or sorry, the temperature of the heat in minus the temperature of the heat out. Our transfer across the system, right? So what we're going to say is that our Q maximum over here, this is going to be CH max is multiplied by, if we think about this logically, that temperature out in this case should be equivalent to the temperature that was going into our system for the cold line. So this is going to be TH of N minus TC of N. And we're going to call this our C, or actually, you know what? Sorry, I shouldn't have put the H max there, just for the sake of nomenclature. This is we'll call this our C maximum. So that is our C maximum in this case. That is the maximum heat transfer coefficient for our hot line. And we can do the same thing for our cold line. We can say that this is, let's see here. This would be the cold temperature out minus the cold temperature in. Right, this is the what it is at the very end of our system once the cold line has been transferred over C minimum in this case, which this one is going to be TH of N minus T C of N, which is basically saying that it is the same as the hot line coming in this case, would be the maximum transfer of heat. So we will call this our C minimum. So the way this is related with NTU is what NTU is as a equation. NTU is the universal heat transfer coefficient multiplied by the area of our system over C minimum. So if we know C min and C max are equivalent, what we can say for the actual max of our system for efficiency, we can say that NTU in this case is a function of the efficiency of our heat mass transfer system and fraction of, or sorry, I shouldn't say the ratio, the C minimum over the C maximum. And once you have derived that, you can then get the overall efficiency of your system, which to relate that back into NTU means that you can figure out the size that you need your system to be to maximally transfer as much heat that you want with your co-current or your counter current. So that is how we can use NTU in conjunction with C minimum and C maximum ratios for sizing heat exchangers.